Great. Okay, so today I'll give a talk on these recent line of works, which are known as VOLE-based ZK, where VOLE stands for this long phrase, vector oblivious linear evaluation. We'll see what these are. Okay, so let me begin by describing what a zero knowledge proof is. So here we have Alice, the prover, and Bob, the verifier. Alice has a private witness W, and we have a public circuit C, and the prover wants to prove that C evaluated on W leads to 1. And think of the circuit as being an arithmetic circuit consisting of some multiplication and addition gates. So obviously, the verifier wants a proof for the validity of the statement, and the prover wants privacy of the witness. So we have these three usual requirements. Completeness says that if the prover is holding a valid witness, then the verifier at the end of the protocol should output, yes, I believe you. Soundness says that if the prover is malicious and is holding a witness which is not valid, then the verifier should output, no, I don't believe you at the end of the protocol. And zero knowledge says that for an honest prover interacting with potentially malicious verifier, the protocol should not leak anything except about the witness, except the validity of the statement, which is the circuit evaluated on witness W leads to 1. So we all are mostly familiar with these three requirements. And now the idea behind these new line of works is to do zero knowledge proof in a pre-processing model, where the protocol is divided into two phases. The first phase is called offline phase, and this can be thought of as an input independent phase, where the witness is not known and even the circuit is not known. So in this phase, the prover and verifier, and they interact and produce some kind of correlated randomness. And then in the online phase, when the prover has a witness W and there is some public circuit C, and they want to, the prover wants to prove that C evaluated on W leads to 1. The prover and verifier can consume these correlated randomness that were produced in the offline phase and interact in a protocol at the end of which verifier outputs the final verdict. So why do we want to do this at all? Like, why do we want to split a zero knowledge proof into these two phases? And the main reason is efficiency. So turns out that if you pre-process things ahead of time in your offline phase, then it can let you achieve online efficiency in terms of communication, rounds, computation, and so on. Okay, so, and this might also remind you of the popular paradigm in MPC, where we do this offline-online split. We pre-process something before we know the private inputs, for example, beaver triples or random OT correlations. And this lets us do very efficient online MPC. So the question here is, obviously, what is the right kind of correlated randomness that we should produce to enable highly efficient zero knowledge proofs in our online phase? Okay, so these recent line of works, which I was terming as VOLE-based ZK line of works, explore a specific kind of correlated randomness that you can leverage in the pre-processing phase. So let's see what that is. So this correlation is called oblivious linear evaluation. And think of it as a generalization of oblivious transfer, but to the arithmetic setting. So recall that in oblivious transfer, you have a sender and a receiver. Similarly, here you will have an OLE sender and OLE receiver. And instead of bit strings, we will be operating on some field F. So the OLE sender has two field elements, A and B, and OLE receiver has a choice. Think of this X as a substitute for the OT choice bit. So it has some value X, and the OLE simply outputs a value Y to the receiver, where Y equals A times X plus B. So this relationship might seem very familiar with the OT relationship. And another way to view this is to think of Y and B as forming an additive secret sharing of A times X. So any questions up till this point? Okay. So this is a simple kind of correlation, and turns out this would be very useful. You can define like different variants of this OLE functionality, one of which is called random OLE. So here, instead of taking chosen inputs from the sender and receiver, the functionality, random OLE functionality, will internally sample all the values uniformly at random, A, B, X, and Y, subject to this constraint. So think of it as a variant of the random OT functionality, where sender and receiver inputs are sampled randomly. And then you can also define a vectorized variant of this random OLE functionality, where the A, B, and the Y, these are vectors of length n. But the value X is still a single field element. And the relationship now holds over vectors of elements. Okay, so it turns out that all these VOLE-based ZK line of works, what they are doing is they are leveraging this specific kind of VOLE correlation. So we'll call such values A, B, X, and Y originated out of this random VOLE functionality as VOLE correlation. So what these VOLE-based ZK line of works are doing is that in the offline phase, they are generating these random VOLE correlations between the prover and the verifier. Looking ahead, the prover would be the VOLE sender and the verifier would be the VOLE receiver. And turns out that in like last 5 years, there has been a lot of works which tries to study how you can generate these random VOLE correlations very efficiently. And the punchline here is that if you want to generate a random VOLE correlation of, let's say, length n, then it only requires communication which is sublinear in n. And if you want to generate many such, so that's the main efficiency benefit that you get. So your communication does not scale with the length of the vector. And this is done using these recent line of works, which are termed as pseudo-random correlation generators, PCGs for short. So we'll not go into the details of how that is done. We'll just use that as a black box and see how it can help us for doing efficient zero-knowledge proofs. Okay, any questions up till this point? Okay, so what we'll
just summarize how even basic OLEs work. Like, yeah, you've been careful not to say really how these are constructed, and the idea of like, well, I almost basically just have in mind the simplest OT, that kind of protocol as how to go about random OLE. And is that like appropriate for your scenario? Like that sort of approach is okay. Maybe Fiat Shamir is okay. Random oracles are okay. Variants of Diffie-Hellman are okay. Is it understood that the setting that you're in, for example, excludes those kind of constructions, or will it likely rely on something more exotic like pairings or lattices or something?
Right. Okay. Good question. So this sublinear communication is achieved by a new kind of not new, but these LPN style assumptions, learning parity with noise. These have been known in the literature for 20 years, but recently only they have been leveraged to construct these so-called what they call VOLE extension technique. So the idea is that we know of OT extension, right? So you generate some number of base OTs and using public key operations, and then using just symmetric key operations, you can produce arbitrary amount of random OT correlations. Similarly, the idea is that by relying on this LPN style of assumption, once you have generated a seed amount of correlations, which are not exactly whole correlations, these are something else, then you can expand it into arbitrary amounts of these whole correlations, even without any communication at all. So once you have some seed correlations between the whole sender and the whole receiver, which requires interaction, then from that point on, they can just locally expand those seeds into an arbitrary amount of these whole correlations, arbitrary length of whole correlations without any interaction. So yeah, some of these constructions, so a common ingredient in all these constructions is to use LPN style assumptions, learning parity with noise. It's a variant of lattice LWE style assumption where the noise vector is sampled as Bernoulli instead of binomial. Yeah, and yeah, I don't know if you did you have any other specific question, or did that?
Okay, no, that does it. If I have to think of this as yeah, that these constructions most likely involve lattice operations and they do something analogous to OT
Yeah.
extension.
Right, but
The main operation for a seed, but then the extension goes through. Yeah, that makes sense.
yeah, but note that these are not as inefficient as like FHE style lattice-based constructions. These are much like these just involve simple linear algebra. So these are in fact very fast and have been implemented in a bunch of papers. Okay, so looking ahead, we'll see how these kind of correlations can be used to design a form of commitment scheme in a very efficient way, which will have nice properties as well. So now, for the time being, let's take a detour. So we'll try to construct a commitment scheme now. So obviously, a commitment scheme has a sender and a receiver, and the sender has some value x that it wants to commit to. Okay, so now imagine this new kind of functionality f auth. What it does is it takes a value x from the sender's value x and outputs delta and k to the receiver and some value m to the sender, such that these m, delta, k are sampled uniformly at random, and x is the chosen input from the sender. And the following relationship holds. So the value k equals m plus delta times x. So now a way to think about this is think of this delta as a global key k held by the receiver, and small k as some local key, and think of m as a MAC on the value x. So this might remind you of this construction that we usually see in crypto courses, which is information theoretic message authentication code. So basically what you're doing is the receiver here is holding a pair of values, delta and k, think of them as keys, and the sender will get this value m, which will be the MAC on the value x. So as output of this functionality, now the sender holds this value x that it wanted to commit to and a MAC on this value m, and the receiver is holding keys delta and k, such that this following relationship holds. And just to picturize this, think of like at the end of this phase, X is basically committed. So I'm displaying this X as in a locked envelope in this diagram. Okay, so this concludes our commit phase. In the opening phase, basically when sender wants to open this value X, it just sends X comma M to the receiver. And the receiver just checks whether the following relationship holds, whether K equals M plus delta times X. And it outputs yes if it holds and no otherwise. Okay, so obviously we want some basic properties out of such a commitment scheme. So we want hiding. And one good property about this scheme is that the commit phase doesn't leak any information about the input X to the receiver during the commit phase. And this is information theoretically hiding. Why? So note, let's see what are the values that the receiver is receiving. It's receiving just two values, delta and K, which are individually uniformly random and don't depend on the value X at all. We also have binding. So we want to say that the sender during the open phase cannot open to some value X prime M prime, which is not equal to the original X and M, except with some small probability, which would be in our case 1 over the field size. So if your field is large, then this is good enough. And the high level intuition for why this will hold is because let's say the sender can come up with some X prime M prime, which is not equal to X comma M. Then you can use those values to extract this delta using this relationship. And this will imply that the sender can guess delta. But this can only happen with probability 1 over the field size because delta is private and completely hidden from the sender during the commit phase. Okay, so these are the two basic properties that we want out of any commitment scheme. A nice property about this specific commitment scheme is that it also has additive homomorphism, which means that if you have commitments to X1 and X2, two different values, then the parties can non-interactively derive a commitment to the sum of those two values. Do you see why this holds? So mentally picture two different equations. K1 equals M1 plus delta times X1, and picture another equation, K2 equals M2 plus delta times X2. These equations are linear, so you can just add them up. And the new key would be K1 plus K2. The new MAC would be M1 plus M2. Delta would be common. Think of it as a global key. So we won't be changing delta. If we want to commit to different values, the delta would remain same across all these values. Only the key K and the MAC M would change across these values. Okay, so due to this additively homomorphic property, there are two nice applications. So first of all, it can be used to open a commitment without actually leaking the value. So imagine that in the opening phase, the sender doesn't want to actually reveal its value X. What it can do is we can construct a commitment to a random value during the commit phase and then send a one-time padded value. So imagine that we generate a commitment to some random value R during the commit phase. And during the open phase, the sender just sends X plus R along with the sum of MAC of X and the MAC of R. And the receiver can do the same kind of check on like the new key and the new MAC. So this is one application which would be crucial in our zero knowledge proof setting, because looking ahead, the prover would be committing to wire values using this scheme and proving relationships between the consistency between different wire values. And we don't want to leak the values of these wires, but we do want to do some kind of opening checks. And the idea would be to randomize the commitments before opening them. The second application is that we can do pre-processing here. So what that means is that if let's say you want to commit to some value X, in a pre-processing phase, in an offline phase, you can generate commitments to random values and then de-randomize it during your online commit phase by just sending a correction term, which is, let's say, X minus R. So if R is uniformly random and sender sends this X minus R to the verifier, it will not leak any information about X because this acts like a one-time pad. But due to additive homomorphism, parties can convert a commitment to R into a commitment to X by just adding this correction term X minus R. Okay, and so now we'll move on to the zero knowledge proof protocol. But just to conclude, these kind of commitments can be efficiently realized using what we saw was VOLE correlation, because this is exactly the relationship of a VOLE correlation. And if you think of a random X not being chosen but sampled randomly from the functionality, then that is a random OLE correlation. And using random OLE correlation, you can generate commitments to random values, which then you can de-randomize using this second application that I mentioned, and thus achieve this kind of commitment. Okay. Any questions up till this point? Because now we'll move on to the zero knowledge proof protocol. And here we'll
there's a way in which these seem like
yeah.
Can you kind of compare these more with like the random masks used in like secret sharing, like not specifically beaver triples, but I mean this seems very much like the random masks used for like MPC input, for example.
Yeah, so these actually a better analogy would be these authentication tags being used in speeds line of work, where you have shares of some value and also shares of delta times that value shared across all parties. And the idea is that basically you're attaching an authentication to every private value in a way so that if these values are modified, then they can be detected efficiently during your protocol. So like if you recall how Speeds gets this malicious security, it's basically exactly the same technique. And this VOLE-based ZK line of works is inspired from those Speeds line of work, specialized to the ZK setting. So Speeds line of work is targeting a more general setting where you want to do MPC. And zero knowledge is a specific kind of MPC functionality where you can choose to have delta, which is the global key known to one of the parties receiver. And all the private values, the X's, are known to one of the parties, which is the prover.
Does it have any application in Shamir sharing? Like, yeah, I mean, the analogy, I'm familiar with how those max are used in speeds, and I know that we don't use max the same way in Shamir sharing, but it looks like it should be conceivable as well.
Yeah, I think it can be used. I think so if you want statistical security in the n/2 setting, then I think that's how they do it. So they attach, what you do is you attach authentication codes to your values of your values which are secret shared. And then if you want to do reconstruction, there is a small statistical probability similar to this 1/f probability, with which except with this small probability, you can detect if someone is trying to maul a share and trying to announce a bad share. So, and you can basically eliminate those bad shares and then do the reconstruction. This is how it is usually done in the n/2 setting where you can't do error correction.
Yeah, that's cool.
Okay. Okay, so now we have seen how to do a simple, how to design a simple commitment scheme using these VOLE-based correlations. So now we'll see how to do the zero knowledge proof protocol. So okay, recall that we have some public circuit C, some which is arithmetic circuit consisting of addition and multiplication gates, and some witness wire values. So we will perform the protocol in two steps. So first would be where first stage would be where we ask the prover to commit to the input and the output of the circuit. And then the second step would be to establish consistency between the output and input. What we want to make sure is that output was indeed derived by computing the circuit on the input values. But it's not clear how to do this directly because our commitments are not fully homomorphic, right? So it's not clear how, like once you commit to input and output, how do you establish relationship that the relationship holds under the hood of commitments, right? These values are not in the clear. So what we'll do is instead of just having commitments to the input and the output, we'll also have commitments to the internal wire values of the circuit. And the idea is that once we have commitments to the internal wire, then we can establish consistency between the input and output wires of each gate in the circuit individually. This is a much simpler task than establishing consistency directly between the output wire of the entire circuit and the input wire of that circuit. So we'll do this gate by gate consistency check, and that will ensure that if each gate consistency check passes, then that will imply that the output of the entire circuit is consistent with the inputs. Okay, so first we'll see this part, the commitment to the input and output plus wires. Okay, so we have Alice and Bob. Alice is the prover holding some witness W, and Bob is the verifier. So as a first step, as I said, we'll label the internal wires as think of these as auxiliary witness values. So we'll have these additional witness values, which are values of the internal wires. And the prover will commit to each of these wire values individually. So think of these as locked envelopes, the commitments. And just looking inside it a bit, we'll use the VOLE-based commitment schemes that we saw in the previous slides, which means that for every commitment to a value W1, Alice is holding W1 and a MAC M1. Bob is holding a key K1 and a global key delta, such that the following relationship holds: K1 equals M1 plus W1 times delta. Okay, so now one observation is that since these commitments are additively homomorphic, we don't actually need to do an explicit commitment to the output wire of addition gates in the circuit. Why? Because those are implicitly already can be derived by just adding the commitments of the input wires. So if you add up the commitments of W3 and W4, you can already derive the commitment to W7. So you don't need an explicit commitment from the prover for the output wires of the addition gates. So this can be removed. Okay, so now we have seen how to do the commitment part. Now we'll see how to do the proof part, where we do the consistency checks. Okay, so recall we have this state for now. We have the circuit and the prover has already committed to all the input wires and the output wires of each multiplication gate in the circuit. Okay, so we want to do gate consistency check, and we have two types of gates. We have addition gates, we have multiplication gates. And as we mentioned, since these commitments that we are generating are additively homomorphic, we don't need to do any explicit check for addition gates because we don't even have an explicit commitment for the output wire of such addition gates. But for multiplication gates, an explicit check is needed because we have an explicit commitment to the output wire of such multiplication gates. So for example, in this diagram, if you look at this particular multiplication gate, we have commitment to W1, W2, and W5. And we need to make sure that W5 is indeed W1 times W2. Similarly for this other multiplication gate. Okay, so now let's just zoom in to this simpler problem where we want to check consistency for a single multiplication gate. So now forget about everything. Just imagine this simple multiplication gate which has internal input wires W1, W2 and output wire W3. And assume that we already have generated commitments to the input and output wires, which means, okay, so this actually turns out to be the most non-trivial part of all these VOLE-based ZK line of works. And different works have come up with different techniques on how to do this consistency check. And everything else apart from this mostly remains the same in all these papers. So for example, this one of these papers called Wolverine, it uses a bucketing style approach analogous to some of these speeds line of works to do this triple check. And this another recent work called Quicksilver does some kind of low degree check. And turns out that this is quite efficient and even simple to describe. And this is the check that we'll see in today's talk. Okay, so now we'll see how to do this consistency check for a single multiplication gate. Any questions up till this point? Okay, so we already have commitments to the input and output wires of this multiplication gate, which means that let's just open up these envelopes. So commitment to W1, what that means is that the prover is holding W1, M1, and the verifier is holding K1, delta, such that the following relationship holds. Similarly for W2 and W3. Okay, so we have these three equations. Okay, so now what we want to make sure is that W3 is indeed W1 times W2. So imagine for a second, if your commitments, if these commitments were somehow multiplicatively homomorphic, right? Then what you could hope to do is somehow combine the commitments of W1 and W2 and to derive a commitment to W3. So for example, if this was just addition operation, let's say you just add these two equations, this one and this one, the first two equations, then you can derive a commitment to the sum of two values because the relationship is linear and these commitments become additively homomorphic. So you can derive the commitment to the sum of two values. And if somehow these commitments were even multiplicatively homomorphic, then you can hope to somehow multiply these two equations, K1 times K2, and get some kind of this kind of relationship. For example, M1 times M2 plus W1 times W2 times delta. And this is what we could have ideally hoped for, but this is not what we get. What we get is something different. So if you multiply these two equations, what you get something on the right hand side is different from what you would expect. What you would hope, sorry. So what you get is this. So you have this M1 times M2 term, but you have some degree 2 terms as well. So this W1 times W2 gets shifted onto this degree 2 term, which is delta square. And then you have some other term as well in the delta variable. Okay, so it's not completely clear how to go ahead from this point, but turns out that even this fact that we can get a commitment to W1 times W2 will be helpful. So this is not exactly a commitment to W1 times W2, but it can be thought of as a higher degree commitment. So think of this equation as a higher degree commitment to W1 times W2, where ideally you would have hoped to have W1 times W2 in your delta term, but it's now in the delta square term. So we'll call this kind of relationship as a degree 2 commitment, where the value underlying the commitment is in the degree 2 term. And here I'm indicating it using this orange envelope, which is different from these white envelopes, which you can think of as degree 1 commitments, where the values underlying the commitments are in the delta term. Whereas in this orange envelope, the value is in the delta square term. Okay. So what we want to do is our goal now is to check whether W1 times W2 is indeed W3 or not, and the approach that we'll take is the following. We'll try to check whether the value underlying this orange envelope matches the value underlying this white envelope of W3. Okay, so it's not completely clear how to do this directly because orange envelopes are different from white envelopes. More precisely, in an orange envelope, the value inside the envelope is in the degree 2 term, whereas in the white envelope, the value underlying that envelope, the commitment, is in the degree 1 term. So it's not clear how to do this consistency check. So we have these two commitments, and the goal is to check whether the value underlying this thing, orange envelope, matches the value underlying this white envelope. Okay, so the idea is the following. So what we can do, if we stare at these equations a bit, we can do some kind of trick here. So take the first equation and multiply the second equation by delta and subtract it from the first equation. So basically what we are trying to do is we are trying to shift this term W3 into a higher degree term. So if you expand out this expression, K1 times K2 minus K3 times delta, you will get something on the right hand side. So forget about everything on the right hand side, except let's focus on this degree 2 term. So in this degree 2 term, you have this value, this coefficient, W1 times W2 minus W3. And the idea is that you can think of this relationship implied by this equation as a degree 2 commitment to W1 times W2 minus W3. And if indeed the prover was honest and it was committing to value W3, which is W1 times W2, then this degree 2 term would vanish and the expression would become something like this. So here you no longer have any degree 2 terms. And this expression can be thought of as a degree 1 commitment, where you can think of the left-hand side as some key capital K. Note that this is something that the verifier can compute locally because it knows K1, it knows K2, it knows K3, and it knows delta. You can think of this term as a new MAC, let's say capital M, and this as some modified witness value, let's call it capital W. And what I'm claiming here is that the prover has capital M and capital W, the verifier has capital K, and together they hold a commitment to this capital W, a degree 1 commitment to capital W. If this relationship W1 times W2 equals W3 indeed holds. So the verifier wants to make sure that this is indeed the case. So what it does is it simply asks the prover to just open this commitment, this white envelope enclosing our new modified witness, which let's call it capital W. And we saw how to open such commitments. The prover just sends the value W and the MAC M, and the verifier checks whether the linear relationship holds. Any questions up till this point? Okay. Just a minor point here. So if the prover just sends these values directly, M and W, these might leak information about the witness. So you don't do this opening directly. You do the trick which I mentioned earlier, where you randomize it using a commitment to a random value, leveraging the additive homomorphism property, and open that randomized value. Okay, but let's keep that aside for now. So zero knowledge can be added. Let's not worry about it. Let's focus on completeness and soundness. So in terms of completeness, if W1 times W2 is indeed W3, this check will always pass, because this equation will reduce to the second equation, which is linear, and the honest prover will be able to open to the right values that will get verified. But if W1 times W2 is not W3, then the claim is that this check that the verifier does at the end will fail, except with some small probability. And you can bound this probability by this value, which is 2 over the field size, by a simple application of short-zipper lemma. And the high-level idea is that basically you have a degree 2 polynomial here, and the verifier is holding an evaluation of a potential degree 2 polynomial at a random point. And if the prover tries to do an opening in the case where W1 times W2 is not W3, then this check will pass with probability at most the degree of the polynomial divided by the field size. Okay, so this concludes the multiplication check protocol that all these like this Quicksilver paper proposes. And note that this just in terms of communication, this just requires the prover to send 2 field elements to the verifier. Computationally, this is very lightweight, because you are not even doing any cryptographic operations. Both prover and verifier in the online phase, they're just information theoretic. You are doing some cryptographic operations in the offline phase to generate these VOLE correlations. But in the online phase, you are not doing any cryptographic operations, which is why the selling point of all these VOLE-based ZK line of works is that computationally they are very, very efficient. And the online phase is so efficient that it just matches to the runtime that you would get if you would just compute the circuit in the clear. Yeah, maybe currently it's an order of magnitude higher, but it's much faster than any other kinds of ZK approaches.
Can you go over again computing the circuit in the clear? I mean, it still is somehow bit by bit and with some expansion due to the field size? Or are you saying less than even that?
So I'm saying that all that the prover has to do in the online phase is to just scan the circuit and generate the internal wire values, which it would anyway do if it were computing the circuit in the clear. And then the way it commits to these wire values is just by sending these correction terms. So one field element per internal wire in order to commit to those wires. And then for each multiplication gate, you have to do this check. And the way I described here, it might seem that for every multiplication gate, you would have to send two field elements from the prover to the verifier. And turns out that if you have, let's say, 100 multiplication gates that you want to check, then you don't need to send 200 elements. You can just do a batch check of all those 100 multiplication gates at once, which I have not described in this diagram. The way to do that is to do a random linear combination of all the checks. So basically what the prover and verifier do, if they want to, let's say, check 100 multiplication gates at once, then they form, okay, I don't know if there's any good way to show this, but all these linear equations that all these equations that I showed, you will take a random linear combination of all these equations where the randomness comes from the verifier. So the verifier would send some random value, let's say chi, and then you would just do a random linear combination of chi times this equation plus chi square times the equation for the second multiplication gate and so on. And basically you can compute a commitment to a random linear combination of all these input and output wire values of all the multiplication gates and do a combined consistency check on that. So what I'm getting at is that if you have a circuit of size, let's say if the circuit has 100 multiplication gates, then the communication required is just to commit to the output wires of each of these multiplication gates, which is just one field element. And then this is the communication required for the commit part. And for the proof part, you just need to send two field elements from the prover to the verifier to do the consistency check for all of the 100 multiplication gates at once. And the catch here is that when you do this kind of batch check, the soundness error will increase. So if you have 100 multiplication gates that you are batch checking at once, then this 2 will become 2 plus 100. But if your field size in the denominator is large enough, let's say 60 bits or 120 bits or something, then this will still give a good enough soundness error. Did that answer your question, Andrew?
Yeah, that was fine.
Okay. Okay, so we are almost there. So in the paper, actually, the authors also show how this multiplication check, consistency check protocol that we saw can be generalized to polynomial gates, where you have some input wires, let's say X, Y, and Z, and this polynomial gate is computing some arbitrary polynomial on these input wires. For example, you can have this degree 3 polynomial. And note that a multiplication gate, in fact, is nothing but a special case of a polynomial gate where the polynomial is exactly degree 2. Okay, so I'll just give you a high-level overview of how they do this. So for multiplication gates, we saw that if we have these commitments to input and output wires, Then using these two commitments, W1 and commitments to W1 and W2, you can derive a degree 2 commitment to the product of those two values, which is the orange envelope. And then you do a consistency check between the degree 1 commitment of W3 and degree 2 commitment of W1 times W2. Using the semi-messy maths that we saw. And if you have in general any polynomial gate, think of a specific polynomial gate where W4 is just the product of W1 times W2 times W3. So it's like multiplication gates, but with input arity 3. So if you have commitments generated for these input and output wire values, then using similar ideas before, you can generate a degree 3 commitment to the product of W1 times W2 and times W3. So you can use these 3 degree 1 commitments of the input wire values to generate a higher degree commitment to the product of those values. And then what you do is you do a consistency check between the degree 1 commitment of the output wire, W4, with the degree 3 commitment that you derived of the product of input wire values. Okay, that's it for today. Do you have any questions?
There gotta be some questions.
So you
I've
said
seen bits of this many times before now, but I follow it better, much better from this presentation than before. Yeah,
Okay.
go ahead, Bolton.
you said in the middle that it was like you basically do the same sort of circuit to like you do this like circuit conversion where it's like instead of a circuit with inputs and outputs and a whole bunch of intermediate wires, you just like treat the intermediate wires as part of the witness, which is like the same operation done in like Grot 16 and like Pinocchio and early ones. Can you even like plug are there frameworks where you can just like plug some like circom code into this in principle? I mean, like it's the same operation, I take it.
Yeah, so I mean, you don't have to, I don't think here you have to generate a new circuit as such, because yeah, so this technique is very common where you commit to your internal wires as well and treat them as auxiliary witness. And the reason it is common is because we have no other good way to do consistency check directly between the output of the circuit and the input of the circuit. We have to go through each wire individually and do the consistency check. Now I think you are trying to hint at converting this original circuit into something else, but I don't see what that will achieve in this particular protocol, because yeah, maybe that buys some kind of efficiency when you do it for these other snark-based protocols. Here I don't see, like, even if you convert it to a new circuit, what is that going to buy you in terms of
I think I'm
efficiency?
just asking is like, is it fully compatible with R1CS, right? There's not going to be any sort of overhead from translating from a different arithmetization into the R1CS arithmetization because it's exactly the same.
Yeah, so I think that should be possible. Although, yes, okay, so if you are saying if the constraint system can be just translated to an R1CS constraint system, right? And yeah, I think that should be possible. But
Yeah, I want to talk
my
about
understanding was that in R1C, like the reason you want to translate to R1CS is then you have efficient proof systems designed specifically for R1CS, right? Yeah. Andrew, you had some question?
Yeah, this seems like exactly compatible with R1CS though, right? And that your linear transformations come for free, and then your multiplications are, you can do one multiplication, you don't get like a free array of multiplications, like of arbitrary degree. So, I mean, it seems like you could take any application written for Pinocchio that like compiles to R1CS, and then you could run that in either the ordinary ZK proof mode or in, yeah, this like two-party mode. And yeah, it just made me think of like when one is appropriate for the other and how to think about it. And it's so weird because I'm still used to thinking of essentially running into the same problems of like how to deal with, like you can get a commitment, but then when you multiply them and use a pairing, then it's the wrong degree, and there's like too much. Well, there's all these things to correct for, but somehow you can correct for them. That
Yeah.
like, seems to relate, but this isn't that setting at all. It is like, it is quite different, and the overlap with I mean, like, how does this relate to zero knowledge proofs? What's the right way to think of it? I think it's that if I, like, you could, a zero knowledge proof is like a publicly verifiable version of this. Whereas with this one, the problem is that
Yeah, so
you can,
good.
it's
So
like
this is
non-transferable.
right. So this is the way the protocol that I presented is designated verifier because this delta thing, which I was calling as the global key, has to be kept private to the verifier. It cannot be made public. And there are some extensions which try to make this publicly verifiable. And if you want to look at that, you can take a look at this SOK paper, SOK of VOLE-based ZK, which tries to compile different types of protocols and also has references on how you can make it publicly verifiable. There is also something called VOLE in the head technique, which has come up. And this was one of the recent candidates in NIST signature scheme, where I've not seen how it works, but like what they say is that they do MPC in the head, but replace it using like substitute OTs and using voles. And that somehow buys them efficiency.
I mean, I guess on the implementation thing, and maybe this is part of where Wilson was going, is, well, yeah, I mean, I can think of two places where I might try to experiment with the VOLE-based, protocols in general. And the two choices are either in something like ArcWorks or in something like NOR or CIRCOM. I mean, one's like in the exponent level, but still sometimes it's appropriate for cryptography, like accumulators, because you still do that like in the snark-friendly cryptography mode. The other is like you have to be modifying the underlying protocol backend itself. And it seems like all of these VOLE-based techniques, well, again, they're not a proof system, so it's like
No,
my guess
this
is
is
like
a proof.
ArcWorks would be
VOLE
appropriate.
itself is not a proof system, but the protocol that I presented is a commit and proof system, the one which uses these VOLE-based commitments.
Yeah, designated verifier commit and proof.
Yeah, designated verifier, right? And I think Galva is a company which is implementing all these VOLE-based ZK kind of proofs. So if you want to look at concrete implementations, they have a library now for implementing, which is implementing these different systems.
Well, I mean, so what would it look like to build on ArcWorks? Like, and why wouldn't that be a good fit?
Yeah, I don't see why it cannot be done. I'm just not sure if people are doing it. I think one difference from Snark line of works is that you don't get succinctness in this proof system. So both the verifier work and the proof length is linear in the size of the circuit and the witness. There are some follow-up works which show how you can do square root compression, but I don't think they're still like as succinct as, let's say, Crowd 16, which is just independent of the size of the circuit.
Let's see. So verification isn't succinct, and it's designated verifier, but compared to ordinary snarks, the online cost of the proving time is, vastly faster.
Yeah, it's just almost the cost
Almost
of
nothing.
putting in clear. Yeah.
Mhm.
And you can also do this in a streaming fashion. So you can prove a circuit without having to just get, like, you can just scan the circuit in a topological order and keep proving it in a topological order. You don't need all the internal wire values ahead of time, commit to them. You can do commit and prove gate by gate for each multiplication gate in a topological order, which I don't think is possible in these snark-based techniques, because you do some kind of FFT on the combined, on the full witness set, right?
Do you get anything if you replace the verifier with TEE or something? Like, is that a way of, obviously changes the trust model, maybe you just have it do the work anyway, but
Make it publicly verifiable, you see?
yeah,
What would be cool?
it's like it would be soundness now depends on the legitimacy of the TE, and but privacy shouldn't. So if it fails, then you still have privacy because it was still a two-party protocol with non-transferable malicious security. But if it's broken, then you no longer get public verifiability. So it's kind of just a cheap replacement for yeah, I was going to say for a proof for something that the verifier would do, but there isn't really any way to do that otherwise. It's a substitute for maybe trying to like virtualize the verifier to have like threshold verifier.
Yeah, I think you can even try to. This is something that I'm curious about, and I think it can be done that you can there are these protocols where you have single prover and multiple verifiers. And I think because things are mostly linear here, you can, instead of having a global delta, you can probably have delta which is threshold shared among the verifiers, and then try to do stuff. But I'm not completely sure. I haven't worked out the details. But I think there can be ways to make it into a multi-verifier proof, or even make it publicly verifiable. But yeah, your point about trees is something which might be practically applicable, like if you actually want to deploy this. Because yeah, as you said, soundness now depends on T not getting broken, but zero knowledge still holds, like whether or not T is broken. Yeah, so there is also some similarity. Like obviously, even in Snark line of works, they have this pre-processing, but it's a different kind of pre-processing, right? It's what we call CRS, and then we have different kinds of CRS, structured, unstructured, and so on. And this VOLE-based ZK is exploring a specific kind of, you can call it CRS, but it's what is called as correlated randomness in these line of works, because this more resembles kind of the correlations that you have in Weaver triples, for example, where parties are holding shares of product of some values. So this is not really the kind of correlations that have been explored in Snark line of works, where you have g raised to some public g raised to x, g raised to x square, and so on. And yeah, so I think one good question is what kind of correlations, like trying to figure out what is the exact kind of correlations that you need if you want to optimize for a specific efficiency metric. Let's say if you want to optimize for online computation, then turns out that this VOLE correlation is the correlation that you need to shoot for. And then maybe if you want succinctness, then the structured CRS Groth 16 kind of CRS is the kind of correlation that you want to shoot for. So yeah, different kinds of correlations might help you get different online benefits.
Cool. Anyone else? We're past our hour. We're not on YouTube, right?
We are on YouTube, yeah.
We are on YouTube? Oh, cool. Any questions from YouTube?
I don't think there's anyone watching on YouTube actually though. So
Not yet. But in the future, we'll watch.
post in the comments. Okay, well, I'm gonna turn off the stream in that case.